This spectrogram of a musical chord shows that every note you hear is built from two distinct parts. There is the fundamental frequency, a low-frequency wave that determines the pitch of the note, and riding on top of that are the harmonics, a cluster of higher-frequency overtones. While the fundamental frequency gives us the basic pitch, the harmonics provide the timbre. This unique physical blend of overtones is the reason a cello sounds different from a flute, even when playing the exact same note. This graph, plotting the DIN 45573 standard, shows the relative acoustic power levels of speech and music across the human hearing spectrum. To reproduce these sounds with true fidelity, an engineering system must maintain a flat frequency response from 40 Hz on the low end all the way up to 20,000 Hz on the high end. If an audio system's bandwidth is limited to 700 Hz, it will capture the fundamental pitch of a cello, but it will delete the upper harmonics. Without those higher frequencies, the cello loses its acoustic character entirely. It will sound like a tuba. Engineering for high fidelity requires the physical reconstruction of the entire acoustic signature of reality. Measuring that acoustic signature requires environments entirely devoid of external resonance, like this anechoic testing chamber. In these environments, a harsh engineering reality becomes clear. The most expensive, precision-engineered amplifier is entirely irrelevant if the physical loudspeaker at the end of the chain is flawed. The loudspeaker has the exacting task of converting electrical energy back into mechanical movement. Designing one is an exercise in strict electromechanical systems engineering. Central to this design is a mechanical paradox. A speaker must move massive amounts of air to generate deep bass, but it must also react with near-zero latency to produce crisp treble. No single physical object can do both optimally. True audio fidelity requires a multi-stage, integrated physical chain: the drivers, the enclosure, the electrical crossover network, and ultimately the room itself. This cross-section shows the foundational component of that chain, the moving coil driver. The amplifier's electrical signal feeds into a speech coil, suspended within a powerful magnetic field, typically operating at a flux density of 1,000 milliteslas. The interaction of these fields forces the attached cone to move forward and backward, producing sound waves. To push the massive, low-frequency waves required for deep bass, this cone must be large, heavy, and structurally robust. Conversely, high frequencies require the cone to vibrate thousands of times per second. That demands an ultra-lightweight surface and near-zero latency to prevent distortion. When a large, heavy cone attempts to reproduce those rapid high frequencies, it triggers a physical phenomenon known as beaming. As shown in this diagram, the acoustic energy radiates entirely from the apex of the cone. Instead of diffusing out into the listening area, the high frequencies shoot forward in a narrow, laser-like path. Move even slightly off the central axis of the speaker, and the signal strength drops sharply, destroying the realism of the audio. To achieve full-spectrum hi-fi without beaming, the audio signal must be physically divided into specialized drivers: massive woofers for the bass, squawkers for the mid-range, and ultra-lightweight domes for the treble. Even with specialized drivers, a bare speaker moving in open air will fail to produce bass. As the cone pushes forward to create a positive pressure wave, it simultaneously creates a negative pressure wave directly behind it. Because low-frequency waves are long and diffuse, the rear sound wave simply wraps around the edge of the driver and neutralizes the front sound wave. This front-to-back cancellation destroys the bass reproduction entirely. The simplest acoustic fix is to mount the speaker in a flat baffle board, serving as a physical barrier to separate the front and rear waves. To be effective, the shortest dimension of this board must be half the physical wavelength of the lowest note it intends to produce. A 40 Hz tone has a wavelength of approximately 8.5 meters. Half of that wavelength means a flat baffle would need to be 14 feet square just to block the wave cancellation. Folding that baffle back on itself creates the compact, six-sided box used in modern systems.
This forms a sealed enclosure, trapping the rear wave entirely and allowing the front wave to project into the room unimpeded. The speaker box is an active, mathematically necessary acoustic boundary built to protect low frequencies from physical self-destruction. This technical diagram outlines the step-by-step construction of a 7-liter sealed enclosure. Building it requires strict adherence to specific physical rules. The primary rule is that the internal volume of the box is strictly dictated by the electromechanical specifications of the driver being used. The speaker needs an exact volume of air trapped behind it to act as an acoustic suspension spring. The second rule dictates the depth. The internal depth of the enclosure must be at least 1.5 times the depth of the speaker magnet to allow for proper acoustic loading. The enclosure also demands extreme structural rigidity. Using internal battens, heavy applications of glue, and fiberglass damping material ensures the box itself will not vibrate and color the sound. Finally, the drivers must be front-mounted. The box has to be perfectly airtight, and attempting to service rear-mounted speakers would require breaking the acoustic seal, ruining the enclosure's integrity. This specification sheet details System 24, an advanced array housing 9 separate drivers inside a massive 80-liter enclosure. It combines a single 12-inch woofer, 4 5-inch squawkers, and 4 1-inch tweeters. Wiring this array presents severe electrical danger. Feeding 40 watts of full-spectrum bass power into a delicate 1-inch tweeter will physically destroy its voice coil. The solution is an inductor-capacitor crossover filter network. This circuit diagram illustrates how it acts as a precision electrical traffic cop, dividing the raw signal from the amplifier before it reaches the speakers. Within the circuit, inductors physically resist changes in current, effectively blocking high frequencies and routing the heavy bass energy safely to the 12-inch woofer. Conversely, capacitors block low frequencies, passing only the fast-moving high-frequency energy up to the dome tweeters. In System 24, this electrical division is exact. The crossover splits the signal precisely at 700 Hz and again at 3000 Hz. This graph shows the result of that complex electromechanical integration. Measured from 50 Hz up to 20,000 Hz, the frequency response maintains a perfectly flat, distortion-free plateau. The driver, the enclosure, and the crossover are now a unified machine. Yet their flawless performance is subject to one final external physical boundary. The sound waves finally leave the enclosure and enter the listening room itself. Mid- and high-frequency sound waves have relatively short wavelengths. They are easily managed and absorbed by everyday architectural elements. Carpets, sofas, and curtains all pull energy out of the wave. For these frequencies, the acoustic target is a clean reverberation time of exactly half a second before the sound energy falls to 1/1,000,000th of its original value and dissipates. Low frequencies, however, operate on a different scale. Massive bass waves are virtually immune to standard room furnishings. They pass straight through fabrics and reflect violently off the solid structural walls. The room's architecture acts as the final, unchangeable acoustic component of the entire signal chain. This diagram illustrates the absolute physical limit of acoustic reproduction, the room diagonal law. The longest physical dimension of a room, the diagonal from a bottom corner to the opposite top corner, dictates the absolute lowest frequency that room can support. The room diagonal must be equal to or greater than the half wavelength of the sound. For example, if a room's diagonal measures 14 feet, a 40 Hz wave will physically fit, but a 30 Hz wave is physically too long for the space. If the sound wave is longer than the room diagonal, the bass response is immediately choked off, and the lower frequencies fall away rapidly. Engineering cannot cheat physics to fit a 20 Hz sub-bass tone into a small room, regardless of investment in high-end amplifiers or speaker components. True high fidelity occurs when the electronics, the mechanical drivers, the sealed enclosure, and the room architecture are engineered as a single, mathematically unified system.